Okay, Assalamualaikum and good morning, everyone. So, we continue with our lectures. By the way, I already uploaded completely all the notes that I have for this particular course onto Putra Blast, so you can start downloading them. Okay, so recall what we did the last time. Essentially, what we did was to look at differential forms. Okay, the idea is to look for geometrical objects, so that for which one can actually use in integrals. So remember, so here essentially your integral elements, like your dx and so on, okay, will be replaced by a more geometrical object called differential forms. I think somehow there's a lag in the tablet. Okay, so we have defined differential forms. Essentially, what they are essentially covariant tensors. Okay, so you can see the indices at the bottom. Okay, and they are fully antisymmetric. Okay, so they will replace the integral elements, the one that you integrate. For example, when you do the integration, you have some variables here. Okay, that is now being replaced by differential forms. Okay, so the other thing that we have learned in the last lecture is to consider the idea of a differentiation of these forms. So the differentiation will not be just the ordinary differentiation. So we need to define what we call stereo derivatives, okay, where it automatically include the antisymmetrization. Okay, so remember your differential forms are antisymmetric objects. So all your indices are, if you exchange any pair of the indices, you should get a negative sign. So in order for this also to work for the derivatives, you also include this antisymmetrization procedure with the differentiation that you're supposed to do. Okay, so that more or less what we did in the previous lecture. So today we are going to sort of go through some properties of these differential forms inside integrals. Okay, and you have seen this essentially the two theorems that you have seen before is essentially your Gauss theorem and the other one is Stokes theorem. Okay. So these are essentially special cases of integral theorems that involves differential forms. Okay, so let's do Stokes theorem first. So what we have here essentially, to remember that our problem previously, we remember, suppose you have Rn or some n-dimensional space. Okay, so this is the bigger space, but you want to do to parameterize a surface or a subspace which is p-dimensional. So this p-dimensional subspace will be parameterized by some p parameters. Okay, so the integral that you need in this particular case will involve some kind of a P form. Okay, so the P differential form. So in this case, for example, over here we are considering the case of a surface which is one-dimensional higher. Okay, we are considering the case of one-dimensional higher surface. So in other words, the true thing that you should be looking at is a P plus 1 form, but you are given P form. So a P form would actually work on the boundary of this surface. So the boundary of this surface are given by this symbol, which is like your derivative here. The ds is the boundary of this symbol. So now, in other words, if omega is a P form, it would be integrated over the boundary. Okay, so this is the boundary. So this is a P plus 1 form. And this is, that is a P form. So this is a P form. Okay, this is a P form. And this one is a p-dimensional surface. Which is the boundary of a P plus 1 dimensional surface. Okay. So this is P plus 1, the boundary will be a P dimensional. So it's always the way you do this for applying differential forms inside integrals. So the degree of your differential forms, okay, so in this particular case is P, will always match with the dimension of the surface that you are integrating over with. So P form, then you have a P-dimensional surface. So if I want to have an integral over P plus 1 what you call dimensional surface, in this case, this whole thing, okay, so that will be a P plus 1 dimensional surface. Then I would need a P plus 1 form. Okay, so a P plus 1 form, but you're only given a P form. The only way that you can increase the degree of this P form is to take a exterior derivative of your P form. So that gives you a P plus 1 form. Okay, so now, so this will be the what you call the right hand side of this particular integral, okay, equation, sorry. So this is P plus 1 and this is also P plus 1. Now the equality is actually the thing that sort of gives you the identity thing, okay. So it doesn't have to be true, but in this case you can actually prove that to be true. I will skip, however, the proof, okay, because it's going to be complicated, and I don't think I will be setting any assignment questions or questions for your exam on the proof of the theorems. Okay, so I'm going to skip all these proofs. So we are going to take this equality to be true in our case. Okay, so the idea here is your Stokes theorem is related to a P form integrated over a boundary, which is going to be equals to the exterior derivative of your P form integrated over the bigger surface, okay, the higher dimensional surface. Okay, so that's essentially a generalized Stokes theorem. So let's try to see how this is being realized. So I'm going to skip all this. You can read this for yourself if you're interested in it. So I'm going to just go to the examples. So let's take the simplest case would be a zero form, p equals 0 here. So your omega will be a zero form, and a zero form is essentially a function. Okay. So the one form that you have to get is actually the exterior derivative of this zero form, which is essentially given by your derivative of your omega, or the derivative of your function. So this is just d dx alpha of your function omega. So this, remember, is a zero form, this is a function. So that, if I really want to be more, no, remember that this is not quite correct here. I should be, no, there are no indices here, right? So there should be a dx alpha. So that is going to be the sum. Okay. But the idea is this is now like a tensor, a covariant one tensor, okay, which is a vector, okay, and it's given by this derivative of this function. Okay, so let's try to apply this to the generalized Stokes theorem that we had before. So let's look at the right hand side. Remember, the right hand side is what? The right hand side is essentially the exterior derivative integrated over the p plus 1 dimensional surface. Okay. So in our case, your p is 0. So this will be integrated over one-dimensional surface, which is really a curve. Okay. So the curve is parameterized by a single parameter. Oops, what's happening? Which is given by lambda 1. Okay. So if you take the right hand side just now, this has to be an exterior derivative of this omega, okay, which is now a function. So this becomes a one form now, and it's being integrated over a one-dimensional curve. Okay, so if one looks at what this thing essentially, this is omega comma alpha, okay, and then you have this will have to be remember that this is now has to be integrated over the curve, okay, and the curve is parameterized by lambda. So what one needs is to do a kind of a chain rule. So you differentiate with respect to the coordinates, okay. So essentially you differentiate d omega dx alpha, and then you need to what you call do the chain rule, because your curve is parameterized by lambda, so you need to take d lambda, okay. And then this will be multiplying d lambda here, so that you can actually do the integration. Okay, so that is essentially what we have here, and if you look at that, these are just if you look at this, is just giving you d lambda, which is that. And of course, you know what this is, because this is a total time derivative, total derivative of your function with respect to this variable lambda, which you can integrate easily to give you omega evaluated at your endpoints of your curve. So in this case, suppose that I'm considering this curve. So this will be parameterized by lambda, okay, from some parameter lambda given by lambda 1, okay, until lambda, okay, the lambda 1 is coming from the 1 parameter. So lambda 1 equals to A goes to lambda 1 equals to B, okay, and that defines the curve, okay. So so what happens over here, you do the integration, so you get the integral evaluated at the endpoints. But what precisely is this? You can think of this as the boundary. So this gives you the boundary of this curve. So I can rephrase this thing as the integral of omega over the boundary. But the boundary is now just at 2 points. So in other words, you take omega at those 2 points. So, well, this is just your ordinary integral that you have come across in the fundamental theorem of calculus. Okay, essentially that's when you integrate a total derivative, you get the evaluation of the functions at the endpoint. Okay, so that's not so interesting. So let's look at the case where you have a one form instead. Okay. So I should mention that. So now what happens is this thing is now equals to that thing, which is the Stokes theorem that we mentioned earlier. So this was the left hand side, this was the right hand side. So your fundamental theorem of calculus is actually this special case of a Stokes theorem. Right. Let's look at another slightly more interesting example. We are looking at the case of p equals to 1. So omega is a one form. Okay, so in other words, it's a covariant vector here. And if you recall the thing that I mentioned in the generalized Stokes theorem, the left-hand side will involve the integral of your omega over the boundary of some surface. So in this case, the right, what you call, space to integrate over this one form will be a one surface. Okay, so that would be the integral of omega. Okay, so this is a one form, and now I would need a one surface, which I will take it to be the boundary of some two surface. So in other words, this is the kind of picture that we have. So here we are really thinking in terms of R3. Okay, so you have this container space in some sense that includes all these surfaces and curves. So you have this surface, and the boundary of this surface are given by this curve. Okay. Well, the other thing that I should have mentioned earlier, there is a kind of orientation rule. So in other words, over here, one needs to give a kind of orientation in such a way that the endpoints, in order for us to know what is the sign over here and what is the sign over here, you need to give to define the orientation. Okay, so in this particular case, you are thinking in terms of the final point, the point at the higher end is giving you a plus sign, at the other end, so sort of gives you the opposite direction of this particular curve, so it has to be a minus sign. Okay, so in this case of this one dimensional curve here, so it bounces two surfaces, so this is 2D and this is actually 1D. Again, we have a sense of orientation here as well, sort of following the curve on the boundary. Okay, so we need to define that orientation later on. Okay, so right, so what is the right, so this gives you the left hand side previously, the integral of the omega over the boundary of the surface. The right hand side will be now essentially given by the exterior derivative of your omega, which is now a two form. So the two form, the right space, the right dimensionality of space will be a two-dimensional surface, which is now given by your S. Okay, so let's look at that. So you have an integral over S, the surface of d omega, and remember omega is going to be something which has one index. See, omega I dxi, for example. Okay, there's a much more coherent theory, so that's why I already put this as dxi. But the idea is this is now a vector, so that means I will be considering components like this, which is given by the omega I with the index at the bottom. Okay, so this will be the covariant vector, one form. So if you take the derivative of this, okay, the derivative of this will be something like this. But you also need to make sure that the resultant object, so this can be written as omega I comma j, but what we need, remember when you do the exterior derivative, you want it to be anti-symmetrized, so one needs to have that. So here, okay, so I've done this slightly differently. So this is supposed to be j here, and let me do this again. So I want this to be j, so this is j. So when I do the derivative, with respect to xi, for example, then this is omega j. So this is really omega j comma I. But this one is not anti-symmetrized, so we need to anti-symmetrize that, and that gives you this quantity. So this, remember, is the exterior derivative of your covariant vector. Okay, and that will give you this anti-symmetrized object that involves this derivatives here. Okay, and that has to be taken into account with respect to this is coordinates in the space. Okay, so in this case that will be R3. So your I and J runs from 1 to 3, but the thing that you want to define is just the surface, so you have to take the derivative with respect to the parameters of the surface and then multiply with that sort of element, integration element. Okay, so that is the content of this exterior derivative of omega integrated over the surface. But if you look at this, okay, this actually gives you one of the component of your curl of omega. So if you write the curl of omega with the component k is given by epsilon k I j omega j comma I, or I could have written this in another way, epsilon k I j, so that you don't get confused with these indices here. So I just simply follow this order of indices. There's an I, so that means I take the derivative with respect to I, xi, okay, and then your omega j. It means the same thing. It's just a different way of writing the symbols. Okay, so I can think of that, and if I simply expand, remember that these are dummy index, I and j here are dummy index, so you have to sum. Okay, so when you sum, you're going to get the different ordering, and you'll be able to get these two terms over here. Okay, so in other words, this thing is really the components of your curl of omega. one could write this as the following. Okay? Epsilon kij times curl of omega at the component k. Okay, so one do that and substitute in there. So you need to have the epsilon kij in there, and this one together with the other terms over here will define you the surface element. Again, there's a much more deeper theory behind this, but no, I just want to give you a feeling for what's happening over here. So if you do not really understand how to get this surface element, no, that's okay. Okay, at the moment, you need to do differential geometry essentially to do this. Okay, so anyway, okay, so this whole thing is now the element ds, okay, which is if you look at this, okay, this is going to be a part of what we normally find in Stokes theorem, the ordinary Stokes theorem. Okay, what's this related to? It's going to be related to the left hand side of your generalized Stokes theorem. I have it somewhere over here, yeah, which is going to be that. Okay, so I'm going to skip all this. Again, the idea here is there's a normal to the surface. Okay, so you need to be able to actually it depends on this particular whether this is clockwise or anti-clockwise, yes, and then you can actually define whether this is normal outwards or normal inwards. Okay, but I don't want to go into those complications at this stage. It's just that you have a feeling that okay, all this generalized Stokes theorem just sort of reduced to the ordinary Stokes theorem. Okay, so this is the left hand side. Just now we're just looking at the right hand side. So left hand side is just your one form integrate over a curve, which is given by C. Okay, the C that bounds the curve. Sorry, the C that bounds the surface. So this is really ds. Okay. So this is the left hand side. So this is just the integral C of what? Well, this is just omega here. This is a one form. So I will have a single index over here, and then this will be with respect to the coordinates of your container space, your R3. So I have dxi, but really I'm doing the integral with respect to a one-dimensional curve. So I will have a d lambda here, like a chain rule kind of thing. So you get d lambda over here, and then that corresponds to essentially a line integral. In fact, the line integral has to be closed, okay, because it bounds a surface. Okay, so you bounce a surface, then essentially this becomes an integral over the closed loop C. Okay, so applying the generalized Stokes theorem will give you essentially your ordinary Stokes theorem. Okay, so so essentially the main idea here is the differential form and the exterior derivative will give you the right integral theorems that you have seen before. The other theorem that we have seen before is the Gauss theorem. So the Gauss theorem is going to be slightly different now from the Stokes theorem. To the Stokes theorem, what you have, you define a particular form, say a P form, to be integrated over a boundary of a P plus one dimensional surface. Okay, so here, So previously P form P plus 1 surface. Okay, so this is the content of your Stokes theorem. Now Gauss theorem is different. Okay, instead of a P form here, one consider the dimension of your space, let's say it's Rn, then the omega that you are considering is one dimensionless. Okay, so your omega is now an n minus 1 form inside Rn. Okay, so if I want to integrate over Rn, then I will have to take the exterior derivative of omega. So when you take the exterior derivative of omega here, it becomes a n form. So an n form you can integrate over Rn. So essentially this gives you this. Okay, so this is an n form. This is a volume inside Rn, an n-dimensional space. Okay, so the content is almost similar. So you have a derivative here over the right dimension of space over here. It will be related to your the form without the derivative. So this now is n minus 1 form, but an n minus 1 form has to be integrated over n minus 1 subspace. So in other words, we have a volume here, so you take the boundary of the volume. Okay, so the boundary of the volume over here would be an n minus 1 dimensional surface. Okay, again there will be some derivation over here to actually prove the theorem, but we are not going to do that. Let me just go proceed in the end. So we take the case of n equals to 3, then your omega is essentially a 2 form, okay, because n minus 1. Okay, and then d omega is a 3 form. Okay, so the Gauss theorem is saying you take a 2 form, you integrate over a boundary of the volume, which is a two-dimensional surface. This will be related to the derivative of your 2 form, which is now a 3 form, integrated over a 3 surface. This is supposed to be 3, sorry. Three volumes. So that gives you, you remember our Gauss theorem is just you have a divergence of a kind of a vector field equals to the vector field integrated over some surface, the flux. Okay, so so again, these are just applications of the much more general idea of a differential form and the exterior derivative. Okay, so let's see some application over here. One of the things that we have seen before is the idea of a current vector J alpha. Okay, and your current vector J alpha, if we take the divergence, it's in this particular form. So this is really what? This is d dx alpha J alpha. So if this is just 1, 2, 3, then you have your divergence of your J with components 1, 2, 3. Okay? But we are trying to generalize this idea to a 4-dimensional space-time rather than just 3-dimensional space that you normally deal with. So this now becomes divergence in divergence divergence in 4D. Okay. So one of the things that we have mentioned before is the idea of this divergence. If it's equals to 0, then it corresponds to some conservation of charge. Okay. Really, this is coming from the Gauss theorem. Okay. So remember the Gauss theorem. So this is like your Gauss theorem here now. Your J alpha. Maybe I should write this in this way. Z. So this is now dj. So this is a stereo derivative. So the dj, okay, not this jockey, dj here is now integrated over a 4-dimensional space-time. Okay, and this must be equals to what? Equals to j. So this is a 4 form. dj here is a 4 form. So j will be a 3 form. 3 form. And it will be integrated over a 3-dimensional surface. I hope you can see my handwriting here. Okay, but essentially is just an application of Gauss theorem in 4 dimensions. Okay. So what does it say? I have this must be equals to this, and this is related to the divergence over here and must be equal to 0. So this integral will give you kind of a 0 thing here, but where is this conservation of charges coming from? Because your 3-dimensional surface has to be a boundary of your 4-dimensional surface, 4-dimensional volume. Okay. So in this particular case, you can think of as follows. So you have a space-like surface sort of bounding, so in between here, so this becomes out your 4-dimensional volume. The boundary, okay, the boundary is a 3-dimensional. In this case, we're taking it to be a space-like surface. And there are 2 of them. One at the beginning, say, a space-like surface. Remember, the normal to a space-like surface will be a time-like vector. So this is going to be a time-like vector, which is normal to a space-like surface. Same thing over here. On this particular part, your normal is actually that. Okay, because it goes from depends on the orientation of that surface. But the idea is now I can rewrite rewrite this part as the integral of your j over the boundary. So the boundary is now essentially that. Okay, the union of these two space-like surfaces. Okay, so if this is actually equals 0, then it says that okay, the integral of this over these boundaries, which is now 2 separate surfaces, 3-dimensional surfaces over here. So this is just like saying that okay, I have it's actually down here, so I can rewrite that. Okay, remember that this is the boundary of the 4-dimensional case, so it will be thinking of this as the boundary. So I will have S2 here as the top one and S1 as the bottom one. So with different orientation. So here is the positive one, this is the negative one. So I'll be able to get this. And this difference over here will be related to your dj over here, which is related to your divergence. Okay, so dj here is going to be equal to 0. So this quantity minus this quantity will be exactly equals to 0, and that tells us whatever this quantity is supposed to be represent, okay, is essentially telling you this quantity is the same, okay, and that essentially the idea of the conserved quantity or conserved charge. The charge is essentially defined as that. Okay, so there are many different charges one can describe in this particular manner. Okay, so we will look at it at some point. The one that we have probably have seen before is the case of your J to be your current flow vector related to your electromagnetic field. Okay. There is another thing that one can actually do is to consider the case of a particular surface, say x4 equals constant. Okay. So that will give you this kind of surface over here, which is, no, this is just like, how should I say, the normal to this is essentially this 4 vector with a non-zero component over here. So it points along time. So this is just like before. So you have a time-like vector here, and this will be some kind of a space-like surface. Okay. But instead of considering the boundaries that bounds a volume, we just consider just this particular surface. So I have that J alpha ds alpha. So this is now a three-dimensional volume element. Okay, which normally we write in this particular form. Okay, so we write that, and there will be some normal here, which is related to this normal. Okay, so now what one can actually do, putting n alpha to be of this specific what you call vector with zeros for the first three components, then the only non-zero component is the fourth component, so I will have J4 over there, and J4 will be integrated over a three-dimensional volume element over this constant surface, okay, and that J4 is essentially related to the idea of a charge density. Remember, if I'm not mistaken, we defined what was that, rho V, rho C. Okay, so that rho C is just getting the right dimensions, and that rho is essentially your charge density. Okay. All right, I think that's it for this lecture. I do not want to go to the proofs, so let me just go to the next, just to begin a little bit. The main idea of introducing these differential forms, as I said, was to make sure we have a geometric object to describe integrals. Okay, so where these integrals are going to take place will be your Remember, we are talking about action principle previously. The action is actually integration of your Lagrangian density. Okay, previously we had something like this. Okay, we talked about fields. Previously we think of your L as d3x. Okay, so this gives you your Lagrangian, right? This is your Lagrangian density, the curly L, and then to get the action you have to integrate over t. So in other words, this is integration of L dt. So here we are making this thing separate. Your spatial part is separate from your time part. But now what we want to do is to make this thing treated as on equal footing. So this becomes Lagrangian in the four-dimensional sense. The Lagrangian density integrated over four-dimensional volume. So that was the main idea of this. So that this now will be written in terms of your differential forms. Okay, and we would like to extend this idea to include fields. Okay, so you have your fields over here inside your Lagrangian density as your variables. Variables for Lagrangian density. Remember, but now it's been treated in much more four-dimensional sense. Previously, we sort of separate it out. Previously, we had something like this. Your L is your fields, function of your fields, and then function of your three-dimensional derivative, and then you have your time derivative. Okay, so previously we treat that way, now we are treating it in a four-dimensional sense. Okay, so doing so, we can always use the variational principle to minimize the action. So since now I only have your two types of these variables inside your Lagrangian density, so I will vary with respect to your variables over here, so your phi a and phi a, and then your derivatives, your four-dimensional derivatives, your phi a, and then the variation over the fourth derivative, so the four derivatives of your fields a. Okay, and again, what do we do in this particular case is try to make this whole expression to be just involving, no, you want to make this as a common factor so that you can bring it outside. So what do we do in this particular case? We take the integration by parts for this one, okay, so that you have a total derivative over here minus your derivative. Now, rather than x on your variation of your fields, you will now act on this partial derivative. So it becomes this one is now a total derivative in four dimensions. Okay, so one can simply integrate out, and then we are going to use Gauss theorem to say that, okay, the variation over your boundary of this four-dimensional volume, okay, is going to be fixed in such a way that your variation is actually equal to 0. So that's where the Gauss theorem comes in. So once this is actually removed, okay, then we can set this to be equal to 0, and then that gives you what we call the Euler-Lagrange equations, which is the equation of motion for the fields. Okay, I think I probably want to stop that here. So this is now the needed equation, the needed equation for the fields. And we are going to apply this to two types of fields later on. One is a scalar field. The other one will be a vector field, which is coming from your potentials for, should not put that arrow here. So there will be two types of examples that we want to do. One is scalar fields. The other will be a vector fields, which is coming from your four potentials, E alpha, okay, for your EM field. So we will do this probably tomorrow, and then we finish off the whole course until lecture 20. This is now lecture 19. Okay, so that's it for today. Go to get your attendance. Okay, the other thing that I've done, I've already shared the SCL folder. So I will unshare the folder by Friday. Okay, so please submit before Friday afternoon, for example. Okay, I think that should be ample time for you to do it. I believe you have all done it, right? Okay, good. Okay, I end the lecture today here. So thank you, everyone.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.